change topic again, and we move to Andreas Schüler, our third speaker. He is a research associate at the EPFL, and he works at the topic of light and energy, and nanostructured materials are in focus, materials for solar energy conversion, and yeah, nanotechnology. And he will talk about smart materials for daylight management. So we are now going more to the technological side to manage and use daylight in buildings and for energy conversion. Andreas, all yours.
Thank you very much for the introduction, Burkhard. Let me share the screen. So it should be this one. Do you have it on your screen now?
Perfect, very good.
Good, okay. So we have heard how important daylight is for the plants, and the daylight is also important for the human beings. We developed while spending most of our time outdoors. Today we spend most of our time indoors, and it's daylight has a great impact on our well-being, on our health. So we have to care about how we manage the daylighting in our buildings. And I believe that with smart materials, with innovative materials, we can contribute a big deal to this topic. Let me start with an example from China. This is a building with a large part of the facade which is glazed. It's a library in Shenzhen. So this is the outside view of the building. And this is the inside view of the building. So the people might be happy to work with a lot of daylight. However, they have to protect themselves for thermal comfort and also for visual comfort. So how could we manage the daylight? Sun protection is a big issue today in buildings, and it's still an issue where we still have to make progress. If you put the blinds at the exterior, then after some time you can have mechanical problems. If you put the blinds in the interior of the building, then it's difficult to get rid of the excess heat. One good solution could be electrochromic windows. With electrochromic windows, you can control the transmittance on demand, so you can switch it either to a clear or to a dark state, and you can keep the solar energy out in summer, saving on cooling energy. You can also have more solar energy in winter, saving heating energy. You can have also more daylighting in winter, and daylighting is good for our well-being. Now, the problem with, or one of the problems with the previous technologies was that there was a liquid electrolyte which was necessary. And I took this photograph from our building. We installed some years ago a glazing based on this technology. And we could see after some time the outgassing of the liquid electrolyte component, and there were these damages to the edges. So durability is very important in buildings. So it would be good to shift to a technology which is all solid state based, no longer liquids involved, because it's very, very difficult to keep an object tight for tens of years. So how would this work? We would start with a glass substrate. That would be shown here. We would deposit a first transparent electrode here, a transparent conductor of oxide. Then we would put a nanocomposite cathodic layer here. We would put the solid ion conductor, and then an anodic electrochromic layer again, and we need a top electrode, which again is transparent. This looks very much like a thin film micro battery. So when we charge this battery, the lithium ions would migrate from the anode to the cathode, and both electrochromic layers would tint. Now, a device which has been made by our PhD student Olivia in our laboratory looks like this. So there is the cathodic electrochromic layer is based on tungsten trioxide, then is tantalum oxide as a solid ion conductor, and the counter electrode is based on nickel tantalum oxide. And there is the top layer of indium tin oxide. Now, how do we get the ions across this solid ion conductor? Somehow the ions have to find their way through this solid conductor. This solid conductor here, lithium phosphorus oxynitride, is a good example. It's popular from battery research. So you can see the gray little balls are the lithium ions, and one migration path for the lithium ions is the vacancy migration path. So a lithium ion would migrate and just fill up a site here, a vacancy site, and there would be then an energy barrier involved. This energy barrier would then be seen here as a bump in this energy diagram. A different migration path, is an alternative migration path, is the interstitial migration path, where the lithium ions migrate here in between the lattice sites. And there are also energy barriers involved here. And in this case, the energy barriers are a little bit higher, and the dominating migration part is most probably the vacancy migration part. So we have to prepare these coatings, we have to make these materials. This is a snapshot of our laboratory. So we would start by introducing a glass slide into our chamber, this is an introduction chamber. Then we would make coatings onto the glass slide here in this deposition chamber in the center of this installation. And then we have the possibilities for surface analysis. We have electron spectroscopy for chemical analysis here on the right. And we have scanning tunneling microscopy here on the left-hand side. So a great advantage of the system is that we can make a sample and analyze the surface of the sample without taking it out to air. So we have a very good image of the as prepared surfaces. Here a close-up of the film deposition. It's a plasma deposition. So we do have in the center of the chamber magnetrons. Those are magnetic electrodes. We would ignite a glow discharge here. This is a cold plasma, and then we would have film growth here on the opposite side here, where we would put the substrate. In industry, there are similar processes already established today. So in industry, these machines look very impressive. They're very long, so you would have like 100 meters of vacuum. The cathode would be now 3.60 meters long, and the dimensions of the glass panes to be treated would be 3 by 7 meters. So we need to get the lithium into the system. So Olivia developed a lithiation process for that purpose. So we have now a process in order to lithiate our coatings in the vacuum system. So we would start by depositing a tungsten trioxide layer and then inserting the lithium here by a special resublimation process. So this is important to fill up the device with lithium, and then we would continue and build up the other layers so that the lithium is contained in the multi-layered system. And then we can make switching systems here. So this is a spectrum of transmission for the dark state, that is the solid line here, the black line, and for the clear state, that is the green line here. And you can calculate the visible transmittance. This device switches from 63 to 3% in visible transmittance, and the energetic transmittance switches from 59% to about 2%. The switching speed is also important, to the order of 10 seconds. So here we measure the transmittance at one wavelength, 650 nanometers, and we would measure the transition time. And this is really in this time scale. And this is very important also for the application in buildings. The window should switch on the second time scale ideally. So there is also a roadmap where we should go with materials for electrochromics. So of course we want to increase durability. We want to also increase the coloration efficiency. And we want to reduce the switching time. And currently, commercial electrochromics is based on solid materials. This would be in this region here. Then currently we work on nanostructuring these materials, making nanocomposite films. So we would be here in this field. And in the future, we might shift also to plasmonic electrochromics, where we could also have selective switch in the near infrared spectrum of the solar radiation. And in the far future, maybe we would have best control with plasmonic electrochromic nanocrystals. So this technology today is still an expensive technology. It's mainly used in prestigious buildings. Now, it would also be good to find a low-cost alternative to this. And there we have an approach which comes from our research group. So we were inspired by our institute building. Our institute has a glazed facade with a large window for the vision section and a smaller window here in the upper region of the facade for the daylighting section. So we thought about what we would like to have in the immediate case. So in the winter, we would like to have high solar transmittance. We would like to ideally take some of the sunlight and redirect it to the depth of the office room. So not only person A would then have enough light for working, but also person B would have good daylighting conditions. So we would also like to have large solar heat gains in order to save on heating energy and a weak reflection from the building. And this would be a good winter situation. Now in summer, the sun is higher in the sky, and in this case, we still want to have light in the depth of the office room for person B. Now we want to reduce the solar gains in order to have savings on the cooling energy. So we would reflect some of the energy outside of the building, and we would like to provide glare protection for person A. Now, we thought about possible geometries, how to do it, and we came up with the idea to integrate very small micro mirrors into the glass pane. So we would have a set of parabolic mirrors here, and we would have a second set of planar mirrors behind. So in winter, the light would be redirected to the back of the office room. That would work nicely. And in summer, the set of the primary mirrors would reflect and focus the light on the secondary mirrors and then kick out the excess sunlight. So we came up with this geometry after a couple of simulations. Our PhD student André Costro programmed a simulation tool, and we run a large campaign of simulation in order to find this geometry. In between, we have novel geometries with our PhD student Jin Gong. So here we propose to add the mirror, make it a little bit longer the structure, make it the mirror from one structure basically, and have this 90-degree angle here in the corner. And then we would even send this sunlight back to the sky in the awaiting situation. So we would have less of the heat in the street canyon, and we would also have less glare in the street canyon in our cities. So we would like to estimate the potential of this new idea. So we ran simulations, and we were looking here at the horizontal illuminance as a function of the distance from the glazing. And it turned out that in certain situations, in spring equinox at noontime, we have a large increase in horizontal illuminance also in the back of the room. So we really can efficiently send back the light to the back of the room. And this is a great advantage. Now we have to average this over 1 year in order to find the full benefits. And even if we average over 1 year, even with diffuse sky, which is sometimes there, we still have some increase of the horizontal illumination in the back of the room. And this is a logarithmic scale. So this little difference here is still quite considerable in the back of the room. We also care about visual comfort. So we need high visual comfort for both ergorama and panorama. So ergorama, we would call the 60-degree cone here ergorama and the 120-degree cone here panorama. And we would like to avoid excessive contrast differences, especially in the ergorama. So our simulation says that for standard glazing, we have many situations where this high contrast situation occurs, while for the microstructured glazing, we have a much more homogeneous illumination of the work plane. So it's also a good advantage. Furthermore, we also believe that we can have strong advantages in glare protection for the direct glare. So we have to make this, and we have to work out a procedure of making this. We would start with the origination of a master mold. We do this by laser ablation. We create this microstructured master. We would then replicate the master. This is done with UV curable resins. Then we have the replicated microstructure. We would deposit mirror coatings on one side of the structures, and finally encapsulate the mirrors. And then we would have the fully emerged mirrors in our glass pane. So we start for origination, we make a mask for laser ablation, we do the laser ablation in collaboration with EMPA and TUN. And then we obtain this master mold, we will replicate it, and here is a snapshot of the master mold. So we took a polycarbonate sheet and we did this structuring by laser ablation. And already the master mold shows this property of light redirection, which is shown here in the image. We also need good transparency. So here we have a little laboratory sample, which shows clearly that also with the integrated micromirrors, you can read when you look through the sample. And the vision for the need for transparency is clearly there in the building if you think of windows. Currently, we are working on making this bigger. So we have the first prototype glazing just with André Costro and in collaboration with BAS Switzerland. We made 2 weeks ago the first glazing in real size, and we want to put it here in a test building. This is the Nest platform at EMPA campus, the Solace module, and we would like to install the new glazing here in order to test whether it brings some benefits for the users of the building. So let me sum up. For electrochromic glazing, this provides transmission control on demand. There is an improved durability if we use solid ion conductors. It's very important that building materials are stable during the next 25 years or even longer, better 50 years, stability. Then with novel nanocomposite films, we can obtain a higher switching speed and also a stronger switching contrast, which is also very important. For the microstructured glazing, we have the additional advantage that we can redirect the light, so we can have more daylight in the back of the room. We can combine this with the glare protection. We have an improved visual comfort in the ergorama. And we can also obtain seasonal dependent solar heat gains. So saving cooling energy in summer and saving heating energy in winter. This works best for direct radiation. And in a mixed situation, as we have it in Lausanne, it already makes sense. And this is a very cost-effective solution because we don't have to have electricity here. We don't have to have this transparent conductor of electrodes. The system is much simpler. And therefore, now today we think of making it in a roll-to-roll process with BASF Switzerland, our industrial partner, as a cost-effective alternative. So I would like to thank, first of all, our PhD student Olivia Bouvard for electrochromics, and André Costro and Jing Gong for the microstructured glazing. Many important help from some people in the group. We also have collaborations on campus EPFL, which is very important for us. We have collaboration with EMPA TUN, the group of Patrick Hoffmann. We are very grateful for our financial support from the funding agencies. And of course, we are very happy also for this exchange with the industrial partners. Very important here is BASF Switzerland for the microstructured glazing and Sage Glass for electrochromics. And I would like to thank you for your attention, and I'm very happy to answer your questions.
Very good. Thank you, Andreas, for sharing these two interesting stories with us on technological developments. And I'm sure there are a few questions, but let me start off with a very simple practical one. The electrochromic windows are, of course, fascinating and they are used in a way, but there are, and I think your approach to make them as a solid state module is very good. What would be the estimated price of something like this?
So the price today for electrochromic windows is still too expensive. So let me check whether I find some price information here. I even have a slide on this. Maybe I jump. So electrochromic is, so there have been simulations for the town of Atlanta in the States. And they found out that electrochromic glazing would be competitive when the cost is below $20 per square foot.
Mm-hmm.
And so that means that when electrochromic glazing is lower, it becomes cheaper than that, then you can save money by installing electrochromic glazing.
Mm-hmm.
Now it's still too expensive. It's about a factor of 3 too expensive today.
Mm-hmm.
And then there is the question, can we get there? Maybe we can even get there. If you compare to the learning curve in photovoltaics, there is an observation that with increase in production volume, the price get down. And if you look at the prices for silicon photovoltaics, the price dropped enormously in the past. So already in the last 15 years, the price dropped more than a factor of 4 in photovoltaics. And so the factor of 3 in price drop for electrochromics might be feasible. It could be possible. However, today it's still a technology for prestigious buildings. There is an additional value, of course, because in some cases you gain also visual comfort, you gain controllability of the visual ambience. You don't have to have mechanical moving parts. So at EPFL we have some buildings where we have to replace the mechanical blinds from year to year. So there are other advantages with electrochromics. But I believe if you really can make it on the large scale, there might be the possibility that we can reach the competitiveness on the economical.
Okay, yeah, thank you for the estimate that is going. There was one question: is it possible, because some of in the second project you reflect in some part of the light, so but the light is in principle energy, because daylight is a kind of diluted energy. So could you combine this with kind of harvesting energy, so with photovoltaics?
Yes, this would be a very, very good idea. So we would, if we go back to this mirror-like geometry, so the light is reflected by the secondary plane mirror. So it's focused by the first parabolic mirror and then focused on the secondary plane mirror. We could think of putting a photovoltaic element here. It could be either a photovoltaic cell, which we would place in this spot. And in the situation of when we have too much light, we would just produce electricity from this light, from the window. Or we could put something here which somehow harvests and concentrate light. There are also concepts around in order to concentrate light, for instance, luminescent concentrators. So we could think of combined systems. Today we are far from being there, so ideas are around. We have to make it also in the laboratory. However, I think in the future there are many interesting roads to go.
Yeah. Maybe one last question from my side. When putting these mirrors into the window, and you showed the one slide where you look through these glass, it looked not completely transparent. So do we lose some of the vision having these mirror structures in there? I would guess so.
So you don't see the mirrors. The mirrors are too small for being visible. However, what you can see is a small ghost image. The small ghost image is related to the diffraction of the light by the periodic structure. And now the recommendation is that we put mirrors in the top, in the daylighting section. I would put metallic mirrors. Mm-hmm. And these metallic mirrors would be useful in order to redirect the light in the depth of the room. And in the vision section, I would put selective mirrors, mirrors which would reflect only the near infrared. Mm-hmm. So we still maintain the seasonal dynamics, and we would put invisible mirrors, and we would also avoid the glare problem with these selective coatings. Mm-hmm. So there are different types of products then. So if you think of the building envelope, in the lower part, we would have another product than in the upper part.
Perfect. Right. So I currently don't see any further questions right now, and we're also, I think, well in time. Andreas, could you stop sharing your screen slides so that we go back to the normal mode here? Perfect. Very good. Good. So thank you to all of the three speakers on there. I think we have seen a quite nice walk through the different to the topic and looked at it from different perspectives. At least what I take from this hour and a half, that the concepts in chemistry and even medicine, and then also going to biology are not so different. No? So light is used for control, light is used for adapt things. And the technological solutions are there also take on some of these concepts. And I think we can definitely learn from each other, and it's interesting to see how close some of the concepts work, and transferring biological kind of models into technical solutions. Of course, it's always a different solution, but the concept stays in a way the same. So I found this very interesting that there are quite a number of similarities and combined things on there. Right, so with this, we're coming to the end of the virtual symposium. Once again, thank you to the speakers, and also thank you to everybody who joined us. I would like to remind that everything was recorded, and you have the chance to listen to it again by going onto the link on the Daylight Academy website. Please stay in tune for any further activities of this kind of the Daylight Academy. And last but not least, I would like to thank Marion and Lydia, so the two people in the Daylight Academy office who made this all possible and who were behind the technique of this. So with this, I'm closing our symposium. Thank you for joining, and see you next time. Bye-bye.
Thank you very much.
Bye-bye.
Yep.
Bye.